Hi and welcome to Unit 3 Topic 2 Video 5 where we review vector projections. Keep in mind that as you carry through the Unit 3 topic you will need to be able to do some of these things in 3 dimensions. So you'll recall vector projections are about projecting one vector onto another vector. That is, breaking one vector up into its components such that those components are perpendicular and parallel to the original vector. So this is called decomposing. I don't know whether it's called decomposing. I just put that word there. Maybe it's called decomposing. But anyway, hopefully you get the point, and if not, we'll have a look at it now. A can be resolved onto B. So first of all, we resolve A into two vector parts, U and V. Now we'll get to V in a minute, or actually W I'm going to call it. We've got W over here. But we're going to start with U. We want the U component, this is the vector projection, such that U is the part of A that's parallel to B. So we've got U is parallel to B, and we all know that if U is parallel to B, then U equals some constant times B. So that's the parallel law. So A, which is the original vector, is equal to U plus W. W is the perpendicular vector. But U is equal to KB. Hopefully you can see that there. So therefore A is equal to KB plus W, and vector W, which is the perpendicular vector, is equal to A minus KB. But W, remember, is perpendicular by definition to B, so W dot B is equal to 0. That's the rule of perpendicularity. And A minus KB dot B, vector B, is equal to 0. So all I've done here is I've substituted W out for what W is equal to there. And of course we have expansion of the dot product, which we've learned quite recently, and we can expand or distribute this dot product. We get A dot B minus KB dot B. So therefore K is equal to, and this is just a quick rearrangement to get us down to here, well, that's not the pen I'm looking for, that'll do. K is equal to A dot B over B dot B. And this is the rule, this is where it all comes from. Remember, A dot B is a dot product, that means it's a constant, and B dot B is a dot product, that is also a constant, so K is equal to a constant, which we expected. In fact, what we've got here is A dot B over B dot B will be equal to this constant we defined up here. So, therefore, we will have defined what the vector projection of U on B is as just some constant times B. Maybe a reduction in length, maybe an expansion. So, for example, it could be an extension on B. If B is this vector and A is this vector, well then the vector projection is going to go there, and it's going to be longer than B. So we really don't know. So that's our value for K, and this is where our vector projection starts. We can calculate K, and therefore we know the vector projection. Of course, B dot B is equal to the magnitude of B squared. We've seen that previously as well. That comes from our dot product expansion. We call U the vector projection. So U is what we're attempting to find, and U is equal to KB. So therefore U is equal to A dot B over B dot B times vector B, or A dot B over the magnitude of B squared times vector B. So we've got these two forms here, which are nice. Of course, U being equal to, I'm down on the next line now, U being equal to A dot B over the magnitude of B times by B, and of course this should be the magnitude of B squared, so I'm copying it from above, can be expanded, so we get A dot B over the magnitude of B times by B over B, the magnitude of B, and that can be simplified to be A dot B hat times B hat. And that's what's on the formula sheet. And remember, B hat is equal to B over the magnitude of B, and B hat, you'll recall, is the unit vector in the direction B. So that's what we have on the formula sheet, but there are many different forms of this. They're all quite similar, but there are certain things you might or might not know that help with this. The scalar projection, or the resolute, as it's sometimes called, so resolute and projection are kind of synonyms, mathematical synonyms, but we tend to say the vector projection is the scalar resolute. So the scalar projection or resolute is the length of U. It's the length of the vector projection. So a vector projection and the scalar resolute is just the magnitude of the vector projection. So if U is equal to some real number dot B hat. So remember U, if I go back up to the diagram, u is the vector component of A in the direction of B, which means that u is equal to some real number times by the unit vector B. Now that real number is not necessarily k, remember k was just times by B, not the unit vector B. But we do know that the magnitude of the unit vector B, I'll change colours again, magnitude of the unit vector B is 1, and the B unit vector gives us direction. It doesn't really give us, it doesn't add anything to the length. So therefore the magnitude of u, which is the scalar resolute, well that's going to be equal to the magnitude of some real value times by b hat. But we've already got this information. So it's going to be equal to a dot b hat times by b hat. And then we can break that magnitude up into its magnitude components. We get the magnitude of a dot b hat times by b hat. But the magnitude of a dot b hat doesn't really make sense because a dot b hat is just a number. It's our real number. So any dot product will provide some number. And so therefore we get a dot b hat times by 1, and we get a dot b hat. Of course I should go and add all the little vector squiggly lines underneath it all, but you get the point. So the magnitude of u is a dot b hat, or we could write it as a dot b over the magnitude of b. So there's all the information that we need. Additionally, we know that there's our diagram again, and that u and w are perpendicular components. And a dot b hat is equal to the magnitude of a times the magnitude of b hat cos theta, which is equal to the magnitude of a cos theta. So therefore u is equal to the magnitude of a cos theta b hat, which, if I just call your attention to it with this massively long arrow and curled, is the other formula on our formula sheet. That's the vector projection formulas. But remember, you don't have all those formulas, so you have to deal with that. And I would suggest now it's not about memorising formulas, it's about practicing questions with the formulas next to you and getting used to having those formulas next to you. So a quick summary of this, and I've decided not to go into any examples for this one. I've got a different diagram now. A is projected on B. We get U as the component of A that is parallel to B, and W is a component of A that is perpendicular to B, and the vector resolute comes in 5 different forms. There they are. And the scalar resolute, which is the magnitude of the vector resolute, is a dot b hat, or the magnitude of A times cos theta, where cos theta is that angle between A and B. So that's all you need to know, but what you need to practice is applying those rules. All the best.